Hello Internet! Today I want to show you the Node2vec code. We have a COLAB notebook and we have here the official KERAS implementation of Node2vec. We are here in the grand topic of graph representational learning. And if you are not familiar with it, here on the left side you have my COLAB notebook and we will run through the code together. And on the right side you have here the theory, the graph representation learning from Professor Jure Leskovic, Stanford University, and I really recommend you attend his course, or you can watch it live on Stanford Online. The course is called CS224W Stanford.education. Now, I hope that you are familiar with embedding nodes, that just if you are not, while we start here up our COLAB notebook, we load TensorFlow, we import KERAS, we have here our movie data file, and we just load some data. And we implement some functions. So we just have here the data. We have here a data frame where we have a movie ID, a rating for this particular movie, and a timestamp. And then we have, again, another data frame where we have the movie ID linked to the specific title of a movie and the genre. And what we do is now we construct a movie graph. And this graph has a special construct. We create an edge between two movie nodes if in the graph, if both movies are rated by the same user higher than a minimum rating. So all movies rated above, I don't know, 3. The movie rating we have here is up to 5, so let's say 3. And the weight of the edge will be based on a mutual information between the two movies, where this is the formula, and you have X is how many users rated the movie X higher than a minimum rated, Y is how many users rated the movie Y higher than a minimum rated, D is the total number of movie rating, and XY is how many users rated both movies higher than a minimum rated, and this is the edge weight. So this is really easy, the code is really simple, we just run through this and we compute this. Now, step 2, we create the graph with the node in the edges. This is easy, the graph consists, the nodes here are just our movies and the edges we just calculated. We use here the network X Python library to compute this. So we add the weighted edges between the movies and then we construct a graph. And if we do this, I think I already did it, then we have the number of nodes and the number of edges. In our example, we have 1,400 graph nodes, so we will have 1,400 movies, and we have 40k edges between those movies. And sometimes I do just a little visualization, but I just want to know, hey, the connected components, do we have a lot of connected components? How disjunct is this graph? Have a look at the visualization. While we wait for the visualization, you remember the goal of Node2vec is to encode the node in the original network space so that the similarity in the embedded space, this is here, approximate the similarity in the original network. So what we have two spaces. The first space is here, our original network. Then we have an encoder that maps this to a lower dimensional vector space. We call this our embedding space. And in the embedding space, we have, the dot product, the cosine similarity in vector spaces as a simple measure of similarity. And what we do now is, our goal is here to say the similarity in the original network, so the network with the node U and the node V, should be somehow similar to the similarity of the embedding. So we have here the embedded space and we want to calculate the representation, the vector of our nodes that are mapped from the original network space to the vector to the embedding space where we have constructed our vectors for each and every node. So we define an encoder. This means a mapping from the nodes to the embedding. This is our encoder. We define a node similarity. We have here the dot product, and interesting will be what is the similarity measure here in our original network. We will see it is an optimization problem. And then we optimize the parameters of the encoder. So here our encoder will be optimized so that the similarity in the original network will correspond to the similarity of the embedded space. So we have similarity A and similarity B should have a clear relation. So the encoder maps each node to a low-dimensional vector, and the similarity function specifies how the relationship in the vector space map to a relationship in the original network space here. Now, I hope you know the mathematics for this, because we are gonna use the random walk approach to node embeddings. And since we are here, yeah, you can see now my visualization. So I can see here, there's one connected component, there's two connecting components, and then we have our 1,400 nodes. We have here now the main bulk of our nodes here in this connected component. So simple visualization check is always recommended. This looks nice. If you're interested in the node degree, this is very easily done. The average node degree is 57. So what you do next is you create your vocabulary. Now the vocabulary is simply the list of the movie names. And then we have a lookup table where we say, hey, the movie, I don't know, Gone with the Wind will have token 1, the movie whatever will have the next token. So this is simply a lookup table. And now we come here in our code execution to random walk. Here we are also with it here, random walk. So again, remember, we have here the dot product in the embedded in the feature space, where we say this measure of similarity in a vector space should correspond to the probability that the node U and the node V co-occur on a random walk over the network structure. I have a visualization here. So we have a node U, and then we walk over node, walk, and we come to another node. And the probability of visiting the node V on a random walk starting from the node U using a certain walk strategy, we will talk about this later, this can be calculated by a probability. And of course, we want to optimize then our system so that the embeddings to encode these random walk statistics encodes this proportional in relation to the cosine, to the dot product or cosine similarity in the vector space. So this is what we want to have. This is our problem of optimization. And without going too much into the detail, we have now feature learning as an optimization problem. And this is our objective. This is what we want to solve. We want to find the maximum of the logarithmic probability of the node U. This is our starting point, and we want to find the neighborhood where NR is the neighborhood set of the node U. And given a specific node U, and we will run all nodes, we want to learn the feature representation predictive of nodes in its neighborhood. So what we do, we can now have an optimization, softmax parametrization. I hope you're familiar with this. Remember, this is here a probability product. So what we do, we take the log. So we get a sum. We reduce a little bit the computational complexity. And we have the sum over all nodes U. As I told you, we will start in every node and walk around in this network. And then we have the sum over all nodes V that are seen on a random walk in our network when we start from the node U. And the expression is, of course, a softmax expression, you know, the parameterization of our probability here. And what we do, since we have a complexity squared, an order square, this is too computational expensive. So what we do is we have an approximation. And this approximation of our probability is very simple, that we have here our dot product, our sigmoid function, a probability between 0 and 1, and then we have here negative sampling enabled. And as you can see here, we do not run over all nodes, whoops, but we just, run over up to the node k. So instead of normalizing all nodes, we just normalize against a k random set of negative samples. These are our negative samples. If you are familiar with Node2vec, you know that again, negative sampling technique at Node2vec was also applied there. And we will use here the same negative sampling for our Node2vec instead of the Node2vec. So we say sample k negative nodes proportional to a degree. And without going into the details, again, where are we? Overview of Node2vec. We want to embed the nodes with a similar network neighborhood close to the nodes in the feature space. So we have two mathematical spaces, and we have a mapping between those mathematical spaces, and we want to have a mapping in a way that the encoder, our mapping, provides the same similarity in a vector space, which is the dot product, to the similarity in our graph, in our network space, which is an optimization problem. And we frame this goal as a prediction task independent maximum likelihood optimization problem. And you know this, or you can think of this as a loss function. And now here we are with our biased random walk. Here we are now. And this is, if this is a graph, we can have two simple options. And this is important because we will have a combination of both. The red one is just the short version. You just go for one step in each and every direction. There is an edge in your graph. Or if you want to go for a depth first algorithm, you say, okay, can I find a way how to get away as fast as possible? So you have here with the breadth first, you have here your local configuration, your local subgraph, and with the depth first, you have the global structure. And we have now two different parameters. We have a return parameter P and an in-out parameter Q. And these two parameters define, so to speak, if you're looking more or less on the local structure, on the local subset of your graph, or if you also take into consideration the global graph structure. So what we have is a biased second order random walk with Node2vec to explore our neighborhood, our network neighborhood. And remember, the idea is that we know that we started at node U, and then we went to node W. And then if you think here as a circle, giving us an L2 distance, we can say, okay, if we go from W back to S1, we reduce the distance. We can go further away to the node S3. If you have here a circle giving us the distance from the midpoint U, you see this has a further distance. Or if you want the same equidistance here with W, you can say, okay, I just make a sidestep and I have the same distance to S1 here in this little demonstration of this graph. Okay, so we have now two model parameters, P, the return parameter, and Q, the walk away parameter. This is exactly what we have here. We have here the return parameter P and the in-out parameter or walk away parameter Q. This is the visualization if you are here in W. and you go back to S1, or you make just a sidestep to S2, or you say, hey, I want to go out to S3 or S4. And this is the nice, because what we have here in the second order, that we know one step history. We know exactly one step in the history where we came from. So without going into details, this is exactly what we're gonna compute now. Again, the Node2vec algorithm is compute random walk probabilities, simulate the random walk of a length L, let's say 5 nodes, starting from each node U, and then optimize the Node2vec objective using stochastic gradient descent, our old SGD that we know so very well. And no wonder that we have here TensorFlow with the KERAS library, because this is exactly a model where we will train with KERAS and will be very, very fast. So this is it from the theory. And remember our Node2vec objective. This is what we want to minimize. This is our loss function, if you want to see this. So this is exactly what we set out. We optimize the embedding using stochastic gradient descent. This is our function. And we can efficiently approximate this using negative sampling. And this is exactly what we're going to do now here, now on the right side with our implementation. So what we do is we have now a function we call define random walk. And what we have, of course, is our graph. We have our number of walks, we have our number of steps we take, and then we have our parameter p and our parameter q that I just showed you. P and q are our walk away or work farther away parameters. So this is really easy to do. You just start a walk with a random node in the graph, and you say I walk for x, y steps. And I define a function next step. The function next step is simply here defined, where you have your neighbors. You have to compute the probabilities of visiting each neighbors. And this is it. There's nothing more to it. Now, let's choose our parameters, because now we generate our training data. Now, you are free to set your parameters. Let's say I do my p-value is 1 and my q-value is a little bit reduced. It is 0.5. So here we have, if we have a low value of q, which I have, it's smaller than 1, I'm more than depth first step. So I'm looking more, a little bit more for the global structure of my graph. The number of iteration of random walks, my number of walks, let's say is 7, and the number of steps that I take in my random walk, the number of steps, let's say, is 8. So, and then here we go. And then we say, okay, let's activate our random walk function. These are our parameter, and let's do the calculation. And here we go. We have 7 walk iteration. This is quite fast. And then what we're going to do, remember, we are here at negative training examples. We generate the positive and the negative example. And the way we do it is simple. We have the aim of a skipgram model. So this means we have a target. This is a movie in the walk sequence, and a context. This is another movie, another node that we want to find on our random walk. And then we have it weighted, how many times these two movies occur in a walk sequence. And then, when it comes to the interesting part, we have a label. And the label, if 1 is set to 1, if those two movies are samples from the walk sequence. So if they're really within my walk. Otherwise, I set it to 0. And remember, we did a similar thing in Node2vec, where we had also 1 for true and 0 for false. And now we have our set of true examples and our set of false examples of our negative examples. And this is exactly what we do. We have a function generate our examples. What I just told you, we run through those examples. And then we have here our generate example function, where we have the sequences, the walks, the window size, Remember, in Node2vec, we had a shifting window size, is here the number of steps. The negative samples is here, we're given with 4, okay? And the vocabulary size, of course, is the amount of movies in our movie database. So let's run this. Takes a little bit of time. And then we see how many training objects we receive. Remember, we have 1,400 nodes and 40K of edges. And now we have a target of 870K. This is nice. So you remember that I did a video on the TensorFlow data dataset, the data input pipeline, how to optimize it. This is exactly what I showed you in my video on the ETL process. We have a shuffle, we have a batch, and we have a prefetch to optimize here the performance loading between the CPU and the GPU. And we use here the tf.data pipeline auto-tune functionality. And then we say, okay, create my data set. My targets are my targets, then I have my contacts, my labels. This is the discriminator between 0 and 1. I have the weights, the number, how often certain movies are on my random walk, and I have the batch size of my input pipeline. This is it. And now we are already training our skipgram model. And if you are familiar with my movie on Node2vec, the KERAS TensorFlow implementation, this is exactly the same. We have a learning rate, we have an embedding dimension. It takes 64. You remember at Node2vec we had 128 hidden dimensions. I just take 64 because we just have 1,400 different movies. And the number of epochs. Okay, I'm just running here on the CPU version of COLAB. Let's see, is 20. So these are our hyperparameter. And let's have a look at our KERAS model. This is it. Here we go. So we have our inputs. Of course, this is the target node and the context node. And then we have our layer embedding, where we have the input dimensionality is our vocabulary size. The output dimension is the embedding dimension. Then we have a regularizer, and this is our embedding layer. And of course, for the target embedding, we have our embed items from the target and our embed item for the context node. And then what we do is simply compute the cosine similarity, the dot product between the different embeddings. And the way we can do it is here simple. We say here the dot product, you can name it dot similarity if you want, between our target embeddings and our context embeddings. And this is it. And the model is simply keras.model. The inputs is our inputs, the outputs is our logits that we defined here. And this is our model. This is the definition of our model. Then, okay, we can plot it, but for the moment, instantiate the model and compile it. So what we have, hold on a sec. So here we are again. This is where we say, okay. And if we plot our model, it is very easy. This is exactly what we embedded here. We have a dot product where we have now the different inputs from our target embeddings and our context embeddings. And remember, we had either from our label 0 for to be false or 1 for to be a true training examples. And this is it. And if you want to see the model compilation, we use, of course, the standard Adam optimizer with our predefined learning rate. This is not a dynamic learning rate. This is a static, but no problem. And then as a loss function, we take the KERAS binary cross entropy function. And where we see our logits are, of course, true, because this is where we defined it. And yeah, binary because we only have 0 or 1. So this is all that we can discriminate. And then let's say, okay, and here we go. So this is gonna take some time. And when I come back, I will show you the result. And even if you want to see the learning history, how I suppose we have here the loss. Yeah, this is the loss function depicted against the epochs. I see you in a little bit of time. And here we are again. We are coming to an end. We have now almost 20 epochs trained. As you can see, our loss is not really reducing accordingly, but yeah, this is just a demonstration. This is the official notebook from KERAS. I will leave you the link to this notebook. You can download it. You can have a look at it. And this is the plot of the loss, how the loss develops. And you can see, yeah, with the number of epochs increasing, our loss is going down almost in a linear fashion. So now, if you want to have a visualization, we have here, what we want is, of course, we get the layer from the embeddings and we want to get the weights. Remember, in Node2vec, we want to have the weights of the hidden layer. And here we have our embedding shape from our 1400 movies. And as I told you, I have a 64-dimensional representation of those movies. And this is exactly, this embedding is exactly what we are looking for. So, and then you can have here just some semantic query, and you say, hey, I define some movies, compute the cosine similarity between these movies. Well, this is not so interesting because maybe you are not familiar with these movies. Yeah, okay, there is some correlation where they say, but the nice thing is what they do for us. They say, hey, visualize the embedding with the embedding projector. We just have to run this. So this generates us the embedding, the vector representation, and within the metadata TSV, it's a tab separated file format, we get the name of the movies. We just have to download those two, these two embedding TSV, download, and the metadata TSV, yes, save it. And the metadata TSV we have to download too, yeah, save the file. And then we jump to the link here, our embedding projector by Google. This is now, yeah, we can increase this now. And we say, okay, let's load our file. And I will be back with you in a second. So, and now I loaded the file. And what we can do now is we can have either tsnay, we can say, okay, let's have a look. Let's do your clustering, the clustering algorithms. Let's have a look at this. What the learning rate with is maybe a little bit too high. And yeah, this takes some time. But if you wanna have a look for yourself, there's a very nice UMAP presentation. Oh yeah, slowly you can see that there is now some clustering happening. Yeah, there are some 1, 2, 3 clusters. This is the, what kind of movie is this? Spaceballs, Chicago. Okay, I'm not familiar with those movies. But you can see here we have a structure where there are 3 main axes, X, Y, Z almost. But if you really want to have a uniform manifold approximation that is really advanced, I recommend UMAP. Okay, they define 500 epochs. And UMAP does has a little bit different distribution. But you can also say, okay, we have here kind of a cluster, here we have kind of a cluster, and here a huge cluster. So this is what you get. You can have now this graph representation learning for clustering or for node prediction or for link prediction. These are the 3 main tasks. What we do here is we have created our graph. Then we did our Node2vec algorithms. We applied this algorithm and we have here now a clustering algorithm where we can see we have here part of a cluster here and here. I would say this ends the representation. I leave you the link here to the official COLAB notebook from KERAS. This is the TensorFlow implementation. I think if you are new to Node2vec, this is a very nice representational learning code in COLAB. Play around with it, learn about it. you can do a lot of modification of optimization. I hope you enjoyed, and I see you in the next video.